Just 1 minute. So your black one, it is electrostatistics is there. So we'll start from that one. So in the black one, first important topic which you have is what we call a Gauss divergence theorem is there. So that is very important. So we'll start the Gauss divergence theorem. So before going into the Gauss divergence theorem, just we'll know what is electric charge and what is Coulomb's law and all those things we will right. So as we know that what is electric charge, and then after what is electric flux, we'll see then what is electric field, electric lines of force. Okay. And then after we'll move to this Gauss divergence theorem. So just we'll start with the Gauss, what is electric charge here. So I'll write. Do you have any idea about what is electric charge? So first we'll know what is are you able to see this board here?
Yes, sir.
One, it is loading. So we'll start on this one. I'm unable to load my board. One minute. Okay. Anyhow, before getting that board, so we know that according to electron theory, so every substance is made up of atoms, right? Every substance is made up of atoms. Every atom is having centrally heavy portion, which we call it as a nucleus, we call. So the nucleus is containing like a protons, and as well as the neutrons. Okay, so they are having their own masses. So the nucleus is positively charged, and around the nucleus, electrons are revolving in different orbits. So that is what already you know about that one. So the number of electrons in an atom is equals to the number of protons in the nucleus. We know that. So as the atom has equal quantities of positive and negative charges, and hence it is electrically neutral, we can call. Okay. So the number of protons or the number of electrons in an atom is called atomic number, we call. And the mass of the protons and neutrons in the nucleus is called atomic mass number, we are going to be called here. Okay. So that is about the atom, how it has been made up of. So electron charge, if you take, so these electrons which are revolving around the nucleus, we will be calling it as which are having negatively charged. And these charges actually they are quantized. Okay, these are quantized, you know that. So now coming to this next one, Coulomb's law here. So if you go for Coulomb's law, uh, if you are having two charges, okay, if you are having two charges, if these two charges are like charges, if they are, then the charge, they are going to be repel each other. If you have two unlike charges, these two unlike charges are going to be attract each other. So this shows that some force is going to be act between the two charges, whether it may be like charges or unlike charges, you are going to act some force between them. So this force, which is present between the two charges, we will be calling it as a electric force we are going to be called here. Okay. The force which is present between the two charges, we are going to be call it as what? Electric force we are going to be called here. Okay. So this electric force is attractive in case of unlike charges. That is, if you are having a positive and negative charge, then the force which is present between them is a attractive force. Suppose if you are having two similar charges, then the force which is present between the uh, two charges is a repulsive force you are going to be have. Okay, if the two charges are having the same, then it is going to be a repulsive force between them you are going to be have. Okay, so the electric force is attractive in case of unlike charges, and it is repulsive between the like charges. Okay, so Coulomb is a scientist who has been given a certain relation between these charges, that is the force. So he said that the force of attraction or any repulsion between the two electrically charged bodies separated by certain distance, uh, he has been given a law which is called it as a Coulomb's law. Actually, what Coulomb's law states is Coulomb's law states that the force of attraction or repulsion between the two charges is directly proportional to the product of the two charges, and it is inversely proportional to the square of the distance between them. Okay. 1 minute, I'm unable to get this whiteboard here. So as I told that the force of attraction or repulsion between the two charges is directly proportional to the product of the charges, and it is inversely proportional to the uh, square of the distance between them. Right. So get this board so that we can write here. Right. Right. One minute. ఈ హోస్ట్ ఎవరున్నారో కొంచెం ఈ వైట్ బోర్డ్ ని అలో చేయరా? సో ప్లీజ్ అలో వైట్ బోర్డ్ సో దట్ ఐ ఏబుల్ టు రైట్. యూఆర్ అనేబుల్ టు రైట్. Whoever host is present here, please enable this board to write. Right. So all of you able to see this whiteboard here now? Right. Now we'll see this Coulomb's law. Then we'll move to Coulomb's law. Okay. So this Coulomb's law will give the uh, relation between the two charges. That is the force which is present between the two charges. So actually, the force of attraction or a repulsion, whichever it is having, the force of attraction or repulsion between the two electrical charges is directly proportional to the product of their charges. So we can write it as F is directly proportional to Q1 and Q2. So here Q1 and Q2 are the two charges which are present here. So the product is Q1 and Q2. So the force of attraction or repulsion between the two electric charges is directly proportional to the product of these two charges. And similarly, the force which is present between the two charges is inversely proportional to the square of the distance between them. So that is, if we are having two charges, this is the charge 1 Q1 we can take, another charge Q2 is there. This is the second charge Q2. If the separation between them is R here, R, then the product of these charges is directly proportional to the force between them, and the force is directly proportional to 1 by r square here. So therefore, by combining these two, we can write F is proportional to Q1, Q2 by r square. We can write F is proportional to Q1, Q2 by r square here. So here, if we remove this proportionality constant here, so we can get it as F is equals to 1 by 4 pi epsilon naught Q1, Q2 by R square. You can get it here. So here, this 1 by 4 pi epsilon naught value, actually it is equals to 9 into 10 to the power of 9 Newton meter square per Coulomb square. So this is what the 1 by 4 pi epsilon naught value, 9 into 10 to the power of 9 Newton meter square per Coulomb square here. And here epsilon naught is nothing but this epsilon naught is nothing but it is the permittivity of the free space, and its value is equals to actually epsilon naught, whichever we have written. This is the permittivity, and its value is equals to 8.9 into 10 to the power of minus 12 Coulomb square per Newton meter square. That is what we have. Okay. So this is what Coulomb's law. Coulomb's law we have got it as what? Coulomb's law we have got it as F is equals to 1 by 4 pi epsilon naught Q1 Q2 by R square we have. That is the force of attraction or repulsion between the two charges is directly proportional to the product of them and inversely proportional to the square of this distance which is separated. That is what we have. And if you talk about electric field here, next, we talk about electric field. What is electric field? We should know here to study about the Gauss law and all those things. So electric field here. So this electric field is nothing but actually the region surrounded, otherwise the region surrounding an electric charge. Okay. Suppose if you have an electric charge which is present at this point, so the region which is surrounding about this, whatever we call it as an electric field. Otherwise, instead of a charge, if you are having group of charges also, whatever may be the region which is surrounded by that, we call it as a electric field we are going to be called. So in which another charge experiences a force is called electric field. Okay. What is the electric field is nothing but the region surrounding an electric charge or a group of charges in which another charge experiences a force is called electric field. We are going to be called here. Okay. So similarly, we can get the value of electric field intensity, otherwise intensity of electric field, we call it as a E. So this intensity of electric field at a point in the field is defined as the force experienced by a unit positive charge. Force experienced by a unit positive charge is equals to F by Q, here we can call here. So F is nothing but the force which we can measure in terms of Newton we can measure, and Q is nothing but the charge which we are measuring in Coulomb. So Newton per Coulomb is nothing but intensity of electric field we are going to be called here. So generally we can write E is equals to, for a unit charge, if you take, we can write it as E is equals to 1 by 4 pi epsilon naught into Q by R square we can write. So the electric field intensity, we can write it as E is equals to 1 by 4 pi epsilon naught into Q by R square here. Okay. So this is what we have. And then after, we should know about electric lines of force also. So generally the electric lines of force, if you take, so if it is a positive charge, how the electric lines of force will be there means in the case of the positive charge, all the electric lines of force which are present, they are away from this charge. So like this, you are going to have electric lines of force. They are always away from this unit positive charge. Suppose instead of that, so if it is a negatively charged, it is there, then always these electric lines of force which will be towards this, you are going to be have towards the charge. So like this. So this is electric lines of force you are going to be have. And if you have a one positive charge and one negative charge near to that one, so always from positive to negative, the electric lines of force will be there. So like this, electric lines of force will be there from positive, negative, and here from this positive charge, the lines of force will be moving away like this. And in the case of this negative, the electric lines of force will be towards this negative charge. So this is the negative charge which is present. So these are the electric lines of force. And in between positive and negative, the electric lines of force will be from positive to negative charge. They are going to move. So this is what the electric lines of force is there. Some properties also there for electric lines of force. And similarly, if you talk about electric dipole, if the two charges, otherwise the arrangement of two equal and opposite point charges at a fixed distance is called it as a electric dipole. Electric dipole. This if you are having a negative charge and another one positive charge, they are separated by distance of 2L from the center of this charge to this one, this to this. So this is the arrangement of two equal and opposite point charges at a fixed distance is called an electric dipole. We are going to be called. If you want to calculate from this dipole moment also, we can calculate the dipole moment P we can is equals to Q into 2L, the magnitude of the charge and the product of the magnitude of the charge and the separation distance between them. That is P is equals to 2QL. That is what we call it as a dipole moment. We are going to become here. Okay. So now for coming to this electrostatistics here. Coming to this electrostatics here. Okay. So first we'll learn about what is electric flux. Learn about electric flux here. So electric flux is nothing but this electric flux through a surface placed inside electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface. Okay. Suppose this is we are having certain surface, electric surface is there. So the number of electric lines of force which are passing through this surface, we call it as a electric flux. Okay. So electric flux is nothing but this electric flux through a surface placed inside the electric field represents the total number of electric lines of force crossing the surface in a direction normal to that surface. We call it as electric flux we are going to be called. So mathematically, if you want to represent this electrical flux, so phi is the surface, electrical flux phi E we call. This will be equals to surface integral of E dot ds. Otherwise, it will be equals to E into surface. So the scalar product of E dot ds is defined as the electric flux to the surface we have. Okay, that is what electric flux we have. Okay. So then we'll move to Gauss law, which is important. Gauss law here. Gauss law. So Gauss law is the converse of Coulomb's law we are going to be have. Okay. So Gauss law states that the total normal electric flux over a closed surface is 1 by epsilon naught times the total charge Q enclosed within surface. Okay. What is the Gauss law states is, Gauss law states that the total normal electric flux phi E. So generally this phi E, the total normal electric flux phi E over a closed surface is equals to 1 by epsilon naught times the total charge. So phi E is equals to 1 by epsilon naught times the total charge. This is what actually Gauss law. So in order to prove this Gauss law here, what we have to take is uh, we will consider a surface. Here we'll consider a surface here. So in this case, what we are proving is when the charge is within the surface. So the case here is when the charge is present, charge is within the surface. So if the charge is present within the surface, then here we'll take a surface here. So let a charge plus Q, which is placed at a point over here, point O, we have placed a charge plus Q here within a closed surface. This is a closed surface we have, okay, which is a irregular shape here. Now we consider a point P on the surface at a distance of R. So here we consider a point P on the surface here at the point P, okay, so which is the distance of R from the point O, right? So we have considered a point P on the surface at a distance R here, okay, from the O. Now we will consider a small area ds here. We consider a smaller area. This is the smaller area ds which we have considered. Okay, ds we have considered here, smaller area ds we have been considered around this point P here. Now the normal to the surface ds is represented by a vector ds here. Okay, normal to the surface, smaller surface. This is the normal. Normal. Okay, so which is represented by d capital S here. Okay, which is making an angle theta with the direction of the electric field. So this is the direction of the electric field E, is making an angle theta here, which is making an angle theta here. Okay, the direction of the electric field E, which is along the OP, along this OP. Electric field direction is in this direction, along OP. Now, the electric flux d phi E, the electric flux d phi E, which is acting outwards. Okay, the means we have considered a smaller surface ds we have been considered. To that, whatever may be the number of electric lines of force which are passing, we call it as a electric flux d phi E, which is outwards to this surface area ds. And this dfy, that is d phi E, which is given by E dot ds, which is given by E dot ds, which is nothing but E ds cos theta. D phi E is equals to E ds cos theta. Make it as equation 1. Okay. And this theta is nothing but the angle which is present between the theta is the angle which is between E and ds. This theta is between the E and ds we have. Okay. Now, from the Coulomb's law, already we have studied about the Coulomb's law. The electric field intensity E at any point which is at a distance of R from point Q is given by. So, otherwise, we'll write here E value. E, that is E is nothing but what? Electric field intensity or electric intensity E at a point P, which is at a distance of R, okay, which is given by E is equals to 1 by 4 pi epsilon naught Q by R square. Already we have seen this one when we have studied this electric field intensity. So this is E is equals to 1 by 4 pi epsilon naught Q by R square. So we have E is equals to 1 by 4 pi Q, 1 by 4 pi epsilon Q by R square, and this equation from the electric flux for dy is equals to E ds cos theta. So here we'll substitute this E value, here we'll substitute. So therefore, from these equations 1 and 2, we can say that d phi E, in place of E here, we substituting this value. We are getting it as what? Q by 4 pi epsilon naught R square into ds cos theta. Okay, ds cos theta, which will be equals to Q by 4 pi epsilon naught if I take outside because it is a constant. Q by 4 pi epsilon naught is constant into ds cos theta by r square you are going to get. And this ds cos theta, whatever we have, this ds cos theta is the solid angle d omega subtended by ds at O. So at this point, whichever we have, right? So at this point O, at this point O, in this one, okay, this one is a d omega, which we call it as solid angle, which is equals to ds cos theta by r square. So therefore, in place of this ds cos theta by r square, we can write it as a d omega. So now it will becomes d phi is equals to q by 4 pi epsilon naught into d omega it becomes. So next I'll continue here. So it will be, you can write it as d phi is equals to q by 4 pi epsilon naught into d omega. This is equation 3. So d phi is equals to q by 4 pi epsilon naught d omega. So now suppose if you want the total flux, that is through entire whole surface, if you want, then what we have to do is we have to integrate this equation. So if you want the entire whole surface flux, if you want, otherwise the total flux phi E, sorry, phi E, not QE, it is phi E, okay, over the whole surface, or the whole surface means which we have taken a irregular surface, no? In that, if you want this, then what we have to do, we have to integrate integration of d phi E is equals to integration of q by 4 pi epsilon naught into d omega is there. So we integrate d phi E, it will becomes phi E, which will be equals to q by 4 pi epsilon naught integration of d omega are going to get here. Okay. So d omega is nothing but what? Actually, the solid angle. So here the surface integral of d omega is a solid angle subtended by the whole surface. This one, this integration of surface integral d omega is the solid subtended surface at the point O. At the point O. So this value, surface integral of d omega, which is subtended due to the entire surface at point O, which will be equals to actually 4 pi. Okay. So the integration of surface integral of d omega is equals to 4 pi. So therefore, pi E, which will be equals to q by 4 pi epsilon naught into 4 pi here. So therefore, this 4 pi will get cancelled. We'll get it as a q by epsilon naught. So what is that we have got here? Phi E is equals to q by epsilon naught. As we have seen the statement of Gauss law, so the flux through entire surface is equals to 1 by epsilon naught times the q. Q is nothing but the total charge which is present on the closed surface. Okay, this is the derivation of the Gauss law. So here we have considered the case that when the charge which is present uh, inside of what we call the surface, we have considered the charge which is present on inside of the surface, then we have calculated that the flux through the entire surface is equals to 1 by epsilon naught times q. We have got it. Okay. Suppose if the charge which is present is outside the surface, here this also we have to see in the case of the Gauss law here. Suppose if the charge, when the charge is outside the surface. Outside the surface. That means if this is a surface, if you take, okay, outside the surface, if you take here. So here, the charge which is present outside the surface. In this case, what we'll do is, we will take a smaller area at this point and at this point, as well as at this point, at this point. So this smaller area, we call it as a DS1, this is a DS2, this is a DS3, smaller area, this is a DS4 here. So this is the point P we call, this is a point Q we call, this is a point R, this is a point S. These are the, you have points. So now we will take a point outside the surface. We will take a point O where the charge is put. Yeah. Now if you draw here, this. Okay. So this is the surface. Consider. Yeah. And at this point is the surface. At this point, this is the surface. At this point, this is the surface we have. So now we'll calculate the electric flux at all these points, and we'll add so that what is the total flux you are getting, we'll calculate here. Now we'll take the electric flux at point P here. That means at this point. So this area we call it as a DS1, right? So this will be equals to, according to the formula, we know that Q by 4 pi epsilon naught into d omega you'll get here. Okay, Q by 4 pi epsilon d omega you are getting. And here you will get a negative sign here. DS1 is equals to minus Q by 4 pi epsilon naught into d omega. So why we are getting here negative sign means you have to consider always this, the electric flux for an outward normal is positive. Outward normal is positive means at this point it is outward normal. At this point it is inward. Okay, it is inward. That means the electric lines of force are entering into this surface here. They are going out at this point and again entering at this position, and again at this point they are going out here. So at this point, as they are entering, so that is the surface at this point is DS1. So we write it as a minus Q by 4 pi epsilon naught into d omega. D omega is nothing but the solid angle at the point O due to this surface d omega, right? So this is equals to minus Q by 4 pi epsilon. And similarly, electric flux at Q, here. So this will be equals to ds2 is equals to Q by 4 pi epsilon naught into d omega you'll get here. At this point, what it is happening, the electric lines are, force are moving away. That means the electric flux is outward. Electric flux is outward, which we consider it as a positive. Similarly, at the point R, it will be ds3. And again, at this point, they are entering into the surface. This will be, it is equals to minus Q by 4 pi epsilon naught into d omega. Similarly, at the point S, which is moving away from the surface, not entering, ds4, it will be equals to Q by 4 pi epsilon naught into d omega you have. So at this position, it is minus Q by 4 pi epsilon naught d omega. At the point Q, it is Q by 4 pi epsilon naught d omega. At the point R, it is minus Q by 4 pi epsilon naught d omega. And at the point S, it is equals to Q by 4 pi epsilon naught d omega. So therefore, if you want the total flux due to these all four surfaces, we have to add. So that is nothing but ds1 plus ds2 plus ds3 plus ds4. As we have negative sign for this one, the solid angle you are going to get same in all the cases. So it will be you are going to get it as 0. Okay, 0. That means the electric flux when the charge is outside the surface. We have considered the charge is outside surface. So at this point, we have considered the charge Q we have considered, right? Which is outside the surface. Then the flux will be equals to 0. That is, the above reasoning is true for all the cones from O to any surface, however, irregular surface which we have considered. So the total electric flux over the whole surface due to an external charge is 0. So at this point we have considered. So that is what we have. This is about the Gauss law we have. Okay, Gauss law we have considered. Similarly, we can see the differential form of Gauss law here. So generally, we'll find out differential form of Gauss law here. Okay, so we have a differential form of Gauss law. Gauss law as well as these both are important. Gauss law derivation they may ask in the examination. Otherwise, they may ask differential Gauss law also. Actually, Gauss law we have. Gauss law is nothing but surface integral of E dot ds is equals to Q by epsilon naught we have. Okay. So this is the Gauss law we have. From this, we can write epsilon naught into surface integral E dot ds, which is equals to Q. Take the equation 1. Okay. So here Q is the charge which is distributed uniformly over a volume V. Okay. And rho is the charge density if you consider. So rho is the charge density if you consider. Then we can write Q is equals to triple integral because it is a for a volume. It will be rho dV you have. Okay. So rho dV. Q is equals to triple integral rho dV we can write. So already we know that Q is equals to we have from the equation 1. So therefore it will be epsilon naught surface integral E dot ds, which is equals to triple integral rho dV. Okay, rho dV. This we can write here. So now using the divergence theorem, Gauss divergence theorem, which actually converts the surface integral into volume integral. So there is a relation between the surface integral to volume integral. So here the conversion from surface integral to volume integral is there. So therefore, by using that one, surface integral of E dot ds, this is S actually, dot ds, which is equals to volume integral divergent dV. This is the equation number 4. So now substituting this equation 4 in this equation 3, what you'll get here is epsilon naught in place of surface integral, we'll write triple integral divergent E dV, which is equals to triple integral rho dV we have. Okay. So from this, we can get it as epsilon naught divergent E, which is equals to rho here. That implies divergent E is equals to rho by epsilon naught. Okay. Otherwise, we can write this same thing as del dot E is equals to rho by epsilon. So this is what we call it as a differential form of Gauss law. This is what we call it as a differential form of Gauss law. Del dot E is equals to rho by epsilon naught. Epsilon naught is nothing but the permittivity of the free space. Epsilon naught is nothing but permittivity of the free space. So similarly, if you apply this in case of volume, sorry, in case of vacuum, so we can write this as a D is equals to epsilon naught E, we can write. D is equals to epsilon naught E, we can write. So this is in the case of the vacuum. This is what we have what we call a differential form of the Gauss law. So what actually differential form of the Gauss law states is, this law states that the divergence of electric field is proportional to the charge at that point of flux E, which depends upon the magnitude of charge or charge density. It is a rho. This is what you have a, differential form of Gauss law. So after this, we have like in this electrostatistics, the applications of this Gauss law are there. That is nothing but we can find out the electric field due to infinite conducting sheet of charge we can find out, as well as electric field due to a uniformly charged sphere we can find out, and as well as we have so many applications like electric field due to a charged cylinder. All these are applications of Gauss law itself only. Okay. So among that, you'll see some of them which are important. So here we'll see what are the applications we have for you. So this is what we have seen so far. So this is a force which we have seen, an electric field on the surface of a charged conductor. So this we have to see. So then these are the force of lines which already we have discussed. And in the next class, we this Gauss theorem so far we have seen. This is the Gauss theorem, right? So here we have got Gauss theorem, and in the applications of the Gauss law, we'll see uh, this one. Gauss law, intensity of field due to uniformly sphere. This when P lies inside the sphere, when P lies outside of the sphere. So in the next class, what we'll do is we'll see this applications of the Gauss law. There are two important applications out there that we'll see in the next class. Okay. So as time ends now, the class is from 12 to 1 only, no? Right. So we'll stop here. In the next class, we'll see the applications so that they are important. You may getting this Gauss law for a long question, and as well as the differential form of Gauss law for short question. And you may get this applications which we, okay.